Hi there. On the bench today, one of these 3-in-1 devices, a multimeter, scope and waveform generator. This one is the Tooltop ET853C, which was sent in by Banggood for a review. I did not pay for it, so I mark it as a promotion, but as you know, that doesn't stop me from giving you an unbiased review. The key specs are listed on the box, and boy, are my expectations high. This is a 20,000 count multimeter and it has a 20 millivolt range. That means 1 microvolt resolution, DC and AC. And current is equally impressive. 200 microamp range means 10 nanoamps resolution. Resistance to 200 megohm. The scope is rated to 70 MHz single channel or 40 MHz when both channels are on. And the waveform generator is the usual sine, square and triangular waveforms only. In the box we have a USB charging lead, the usual set of multimeter probes, a bag with 2 oscilloscope probes, and a cloth bag for the multimeter. The meter is relatively small, which is a blessing if you have to carry it around, and a curse because of the small screen size, especially in oscilloscope mode. Another consequence is that the scope's connectors are tiny MCX types, meaning normal BNC cables or scope probes won't fit. Let's power it on. I love that this is a standard multimeter with the usual rotating function switch, not a smart multimeter. On first power up you have to select the language. The meaning of the 4 function keys under the display is shown on the lowest part of the screen, so F4 is the OK button. There are a couple of function key options for volts, switching between AC and DC, Hertz, PH stands for peak hold, and rel for relative. Millivolts has the same options and indeed a microvolt resolution. Resistance can be switched to diode mode or continuity and of course rel. Capacitance offers just rel. Hertz offers the option to show duty cycle instead of frequency. The graph on the upper area of the display is a reminder to use the 2 right sockets for this function, which is of course COM and volts, ohms and capacitance. As I switch to the microamp range, this changes to indicate that the middle sockets are now to be used. This is a reminder for people to move the leads. It is not as effective as a mechanical shutter or the input error beep you get, for example, on a Bryman, or even the lighting of actual sockets in some Kaiwitz meters, but still better than nothing. The options in current mode are the same as for volts, which is nice. There's another off at the most right. Well, why not? Pressing menu in DMM mode allows switching between another menu, DMM, OSC standing for oscilloscope, and AWG, which is the wave generator. The A in AWG is actually wrong since it stands for arbitrary wave generator, and this generator can do only 3 predefined waveforms, nothing arbitrary. It is interesting that this is foremost a multimeter. You have to turn it on conventionally using the rotary selector. Only once the multimeter is running, regardless of the selected function, you can then use menu to select oscilloscope or wave generator. To turn the whole thing off, you have to again use the multimeter rotary switch. This meter does quite a light show. Not only is the range switch illuminated, but the 2 bars on each side. Frankly, I would have preferred less fancy lights for a longer battery life, but that's maybe just me. As I feared, the meter may have 1 microvolt resolution, but it can't measure less than 10 microvolts, and even there the accuracy is questionable. My BM869S isn't the greatest for this test either, so I ran this again with the Agilent 3441A, a 6.5 digit meter. The graph shows that the error increases quite a bit at the microvolt level. It's not easy to measure such tiny voltages anyway, because a lot of things like noise and thermal electric voltages caused by metal-to-metal junctions are becoming a major problem at this range. That isn't to say that the 20 millivolt range and 1 microvolt resolution of the ET853C is useless, but it's really more for looking at trends. For absolute measurements, basically 1 millivolt is the low end where you can still have 1% accuracy. From that level on, the meter performed amicably for higher voltages up to 100 volts, which was the highest DC voltage I tested. Testing AC millivolts and microvolts is a challenge in itself. I have to roll out another attenuator because my function generators can't produce the microvolts I need for this test, and the accuracy of my other digital meters is also limited to millivolts. So I added the TM3B analog AC microvolt meter into the setup, starting with 100 millivolts and everything's fine. Going down 20 dB and we're now at 10 millivolts, which is still fine and shows correctly in all three meters. Another 10 dB down to 3.17 millivolts and the priming is now slightly beyond the lowest value where its specified accuracy is applicable. But the ET853C is still going strong. Another 10 dB down to 1 millivolt and the ET53C and the TM3B are showing the correct value while the priming is definitely too low now. 317 microvolts now and the ET53C and the TM3B are still in agreement. 100 microvolts and now the ET53C is starting to lose accuracy. 31.7 microvolt and the meter is no longer reading a value. Similar to the DC millivolt case, it can't really measure down to 1 microvolt, but as long as you're above 100 microvolts, it performs great. Here's the plot of the AC microvolts, millivolts and volts. As I said, as long as you stay above 100 microvolts, there's nothing to complain here, all the way to 750 volts. That is an impressive range and it beats most other multimeters in going that low. Also quite amazing is the performance on the DC microamps and below. It basically tracks spot on with the BM869S. In part that is because at these nano amps both meters have the same resolution and the same number of digits. Only on higher currents with more digits a difference starts to emerge. This is reflected in the graph, but even then the difference between both meters was tiny, so the error stays well below the specs. A great result for the ET853C. And the same is true for AC amps. As expected, the need for RMS conversion prevents the ET853C from measuring quite as low currents as for the DC case, but this performance is still very respectable. The AC bandwidth is specified from 50 Hz to 1 kHz, but my sample had no problems exceeding this in both directions. The 3 dB limit was about 3 kHz. The multimeter leads that come with it are of the usual PVC kind, but at least the probe tips have removable shrouds. I normally prefer not to use shrouds, but in a tight space, with the danger of inadvertently touching something else, they might come in useful. In continuity mode, it takes quite some time before the display shows a resistance value, but luckily the acoustic response is much faster. Even with the probes that came with the meter, no problem here. I already saw this at continuity test. Auto ranging is really slow. 3 to 4 seconds is not great. If you need to measure a lot of similar resistors, for example, consider putting the meter into manual range. Apart from that, resistance mode is quite good and the meter has no problems measuring a 100 megohm resistor. Diode mode works as expected. There is no beep in forward direction and it can light up and measure just one LED, not 2 or more in series. A 1 nanofarad 1% capacitor is measured quite accurately. This should be 500 picofarad, but it's close enough. And this should be 200 picofarad, but okay, it's in the ballpark. No problem in measuring higher capacitors, such as these. Electrolytics also work fine, but as it's common, the higher the capacitor, the slower the measurement. My standard test for this is this setup with two 4700 microfarad cups in parallel, resulting in a total of 9400 microfarad. Let's see how long the meter takes to measure this. About 5 seconds. That's actually not too bad. Before leaving the multimeter, a quick show of the peak hold function that is an option in nearly all modes. When pressing it, the meter records and displays the maximum and minimum peaks while continuing the normal display. You can start and stop and reset the peak hold, which is actually quite a nice and useful implementation. It would be perfect if they also computed and showed average, but sadly no. Onwards to the oscilloscope. We have been promised 70 MHz. Let's see what the bandwidth really is, starting at 50 kHz and increasing the frequency in steps. In the interest of time, I show this accelerated. I only use one channel here, and occasionally I need to change the horizontal frequency as the picture becomes unstable. I did not want to use auto because that also adjusts the vertical settings, and I want that to stay the same during the whole test. The result as a graph. It is quite clear that the -3 dB bandwidth is 40 MHz and not 70, even in one channel mode. Yes, you can still see about a picture at 70 MHz in one channel mode, but the front end of this scope is limited to 40 MHz. Here is a 50 MHz sine wave at 12 nanoseconds per division when both channels are on. Pretty unusable because there are so few samples that producing a reasonable image of the waveform is impossible. If I turn the second channel off, what a difference, a much better representation of the waveform. What happens here is that the scope's 200 megasamples per second is shared between the two channels, as it's commonly done in scopes. When both channels are on, this leaves only 100 megasamples for each channel. At the 12 nanoseconds per division horizontal setting, this leaves just 1.2 samples per division, or 14.4 samples across the whole visible screen. When the second channel is off, the other channel can now use 200 megasamples per second, resulting in 2.4 samples per division. Still not great, but with such a simple wave, the connect the dots algorithm of the scope display software manages to produce a decent image. A more complex, irregular waveform may not be so lucky. Just to point out that in both cases the display actually uses 28.8 samples for the whole picture. Just in the left case, half of them are drawing the horizontal line for channel 2. I don't want to make this video overly long, and the rest of the scope features are what you expect a scope needs to have. Operation takes some getting used to, but it's all there. Of interest is maybe the unexpectedly rich implementation of the measurements the scope can do. Hitting menu in scope mode brings up this screen, and hitting F1 gets you this selection. Waveform allows you to organize and view previously saved snapshots of scope images. I'm not covering this in this video. Voltage gives you a selection of voltage things the scope can measure. Currently enabled are VPP and VRMS, but you can enable or disable any combinations of these items here. Now the average voltage measurement is enabled too. Time gives a selection of horizontal measurements that is time related. At the moment only frequency is selected, but you can have these other too. Together it's no substitution for proper cursors, but it's not a bad feature set. The problem is that the limited screen size forces you to enable what you really need to see at the moment. Otherwise all these readouts cover half of the waveform. Calibrate does the usual thing of realigning the vertical amplifier settings. One should do this every so often, especially if you want to take actual measurements. The only other scope related setting here is grid, which allows you to turn the grid on or off. The other options are the same for the DMM, namely light to reduce the screen backlight intensity, sleep to select the period for automatic power off or disable it as I have done, and beep to reduce but sadly not totally ban the many times the ET853C beeps at you. I already mentioned that unfortunately the ET853C uses MCX instead of BNC connectors for the two channels of the oscilloscope. The probes that come with it are of course equipped with MCX connectors, but if you want to connect something else, for example a 50 ohm through resistor, you need to get an MCX adapter. This is a very fragile setup and stresses the connection, so be careful what is connected there and try not to move the whole thing. The other issue I have is with the wave generator output. It's that little hook in between the two channels. To use it to drive an amp, for example, you can use an alligator clip on it, but where do you get the ground connection? Clearly the intent is to use the wave generator with a scope, and the scope probe just clips into the hook for the generator output, and there you go. No need for a ground connection because the generator and the scope share the same ground. The point of using the generator this way is to compensate the scope probes. For this reason, the waveform generator defaults to a 1 kHz rectangular wave with 3 volts amplitude. That is all fine, but no excuse for not having a proper output of the wave generator, because the generator can do more than just 1 kHz rectangular waves. You can have triangular or sinusoidal. The output amplitude can be selected in fixed steps, with 3 volts peak to peak being the maximum. Sine and triangular waves can have a frequency between 10 Hz and 100 kHz, again in fixed steps. For the rectangular waveforms, the maximum frequency is 5 MHz. This is all very basic, but way more than a simple probe compensation generator, so the lack of a proper output is inexcusable. How this should be implemented is shown at the O1 HTS series of multimeter scope/wave gens. It has a proper output for the wave generator and an independent 1 kHz generator with a hook for probe compensation. Incidentally, it also has a ground there as well, so you can even connect the 1 kHz generator to something else if you want. The ET853C has a built-in battery and is charged over USB-C. This can be very dangerous if the probes are used while the meter is charging, or if the charge lead is still plugged into the meter and accidentally touched. Let's see how this problem is being handled. I'm using the primary multimeter on the left to check the resistance between the measurement probes of the ET853C and the USB connections, and I'm pleasantly surprised that there is no connection, not even a high resistance one. Checking against the scope probes reveals something different though. The ground of the scope probes is directly connected to the ground of the USB port. This is actually dealt with in the manual. It says they have implemented an isolated power supply to ensure that the multimeter probes are isolated from the USB port. They also warn that this is not the case for the scope probes. I'm really encouraged that they are finally going in the right direction. Being cynical, I think they are only doing this with an eye of getting it UL listed. The shrouds on the probes also point in that direction. Well, whatever the motivation, at least the multimeter section is now safe. So how do they do the isolated power supply? Let's open it to find out. On first glance, no screws are visible anywhere, including under the tilting bale. But it turns out that the red rubber bumpers on each side can be removed fairly easily. And that reveals 4 screws, 1 in each corner. Removing them and the case can be opened a little, but something is holding it back. It's a battery cable, but it's possible to unplug the cable from the main board, and the back of the case can now be removed. The battery looks like a standard 18650, but it's encased in some plastic, and the shiny bits on either side seem to be glue or possible welding. Did they seal this battery in? That would be very service unfriendly. But wait a minute, what is this? It looks like the end of another screw. Oh, sneaky. They put a quality assurance sticker on the other side to hide it. Removing the QA sticker reveals a screw. And when removed, the whole tilting bale can be lifted off to reveal access to the other side of the battery compartment. With a 18650 cell that can be easily taken out. It has no whiting on it and it's attached to wires and a plug. I tested the capacity outside the meter and it's just a meager 1450 milliamp hours, so an immediate improvement idea would be replacing this cell with one that has more capacity. I removed the PCB from its case to see what's on the other side. A number of chips are hidden under the LCD and I decided to leave them alone. It may be interesting to see how they do the light show. There are 2 LEDs on either side of the range switch and one shines through a hole in the PCB which illuminates the range switch itself. They had to do it this way because the contact bridge of the switch sweeps directly over the surface. A lot of effort. For what exactly? On the left we have the scope input and the wave generator. The 2 whitish boxes are relays, one for each channel. On the right is the multimeter part. There is some effort on protection, a single MOV and a tracking slot here. The current inputs are protected by fuses, worth a closer look. The milliamp range is protected by that big orange boxy thing, which looks like a poly switch. a resettable fuse. It works a bit like a PDC. If it gets hot by the flow of current through it, it expands and breaks the contact. It reconnects when cooled down. According to the manual, it's rated for 250 volts and 200 milliamps. The 10 amp fuse is an SMD type and soldered in. According to the manual, it's rated at 125 volts, 10 amps. The manual says no word that replacing this fuse needs SMD soldering skills. It just says reinstall and secure the back cover. Nice. The isolated power is using a NSI P8942 chip. This is quite an interesting device that comes in a range of options. All of them have a power section that can transfer 5 volts or 3.3 volts up to 100 milliamps current in a fully isolated way from one side of the chip to the other. The implementation of the isolated data channel varies with the different options. The one used in the ET853C is this one that has 2 channels going from right to left and 2 channels going back the other way. They are digital channels transferring digital data, so think I2C or SPI buses. The chip sits here. How I think this works is that this big chip further down towards the multimeter input basically implements the multimeter measuring circuit, that is the analog part. Sadly, the chip's identification has been erased, so I can't confirm that. The small chip here is an EEPROM. So the architecture is not to isolate the USB input from the rest of the meter, but instead make the analog multimeter front end floating and isolate it from the rest of the meter. You can kind of see the outline of the isolated floating area by looking at the traces and ground planes of the PCB. All communication into and out of the area is done via the 4 isolated channels. This also explains that the oscilloscope, which is part of the PCB more to the left, is not isolated from the USB. While the meter was open, I took the opportunity to connect it to my bench power supply. The yellow fluke shows the supply voltage at the ET853C and the red Bryman shows the current flow from the bench power supply. Well, it did not like that. The reason is that the current is quite high and so the burden voltage of the milliamp range in the Bryman drops the supply to the meter below its operating threshold. This is why you should always measure the voltage behind the current meter, not before. An easy fix is to select the amp mode with its much lower burden voltage and lose a bit of resolution. And try again. This time it works. The current in multimeter mode is quite significant, close to 300 milliamps. Selecting the oscilloscope makes no difference. Same for the wave generator. Turning the flashlight on pushes it to 330 milliamps. Testing the behavior with a low battery. The meter just beeps and reboots in a cycle. The lowest voltage it can handle is 3.4 volts about, which means it can never even use the full capacity of a battery before it shuts down. In my experience, you get maybe 3 to 4 hours of usage per charge. So what's the conclusion? Some 3-in-1 devices like the O1 HTS series are primarily capable scopes with a so-so multimeter attached. I think the ET853C is the opposite. It's a very capable multimeter with an average scope function and a very, very basic wave generator thrown in as an afterthought. The microvolt and nano amp modes raise unrealistic expectations that are not quite fulfilled and maybe are beyond what can be technically done in an affordable handheld meter. So why not going down quite as low as you might expect from the advertising? The ET853C does a great job in its volts and amps modes. The scope mode allows you to do most things as long as you know its limits. Its built-in measurement functions are useful, but the wave generator is probably best relegated to probe compensation. As for build and design, I very much like the way the multimeter is isolated from the USB. This should become standard. If you are on the lookout for a good multimeter with an okayish scope function thrown in, you can do a lot worse than the ET853C, especially if you find it on a sale. I'll leave a link in the description. If you like my videos, don't forget to like and subscribe and maybe consider becoming a Patreon. That would really help this channel. The link's in the description. Thanks for watching.